All right, so welcome to this first very informal introduction to the new upgrade at Upenn, um, where software from 2016 had been updated a bit with some features, has now undergone a complete um, transformation into the software that are used on Zeus 3s. Um, it being a Zeus 2, there are some, let's say, some adaptations, but basically this will work very, very similarly to a Zeus 3 and has all the benefits of that, as well as a newer Linux version. Anyway, what we got here is a direct TeamViewer access to the computer, and we'll use that to show the various elements. The first thing are the software. I'll go through those. We've got a number of software programs over on the left here. Those are the ones that would typically be needed or could be needed. The first one is the X controller. That's similar to how it was on the old system. The X controller brings up the panels that show us what's going on with the detector. It shows us the last taken image because we are not in the process of taking an image at this point in time, and it brings up both the WAX and the SAXS. In the Zeus controller, we've got just one thing coming up, which is spec. Spec FE is no longer available in this. The functionalities in spec FE are now handled directly in spec or in GICC or through the spec command line where you can also execute macros as you could previously. There are a couple of additional views in here. There's a maintenance or some maintenance programs, some communication programs. Let me just see. I think the server is the detector. So if you need to restart the detector software, you can stop it here and start it again. It'll take about 30 to 40 seconds to restart the software if that's needed. There's also Linkum servers here. So this Linkum over here is the Linkum that will be able to control it with spec commands, the LKM commands similar to what you had before. So that hookup should work. And here's the Linkum controller that works with XICC. So on this one here, if one wants to run this, you need to click this here. And if it is indeed connected, then we would see it be allowed to be connected. But it's not at this point in time. It's apparently not on the system. So we'll just go ahead and well, let's wait a second. We'll go ahead and start spec. So spec starts up. Looks just like it normally has, behind the scenes of spec FE, runs through all the motors, then loads in a number of programs. And then once it's done, with all of those programs, it has this little message down here says that everything has been loaded correctly and please proceed, but then it has a timeout of about 10 seconds. With this, we're ready to go. We can jump into doing command line measurements or running macros or whatever, but the main graphical user interface on this system is XICC, where there are three, let's say, overall regions or distributed horizontally. So here we have something that has to do with our samples, locations of them moving around, setting the type of sample containers that we have. In the middle here, we've got in the top something about setting the configurations, setting where to store our data, how do we want the measurement done, and then some direct control, for example, the source, where we can change the source from copper to moly, shutter opening, beam stops, as well as the detector and some region of interest buttons down here. There's also a center detector button, which will move the beam stop out of the way and then do an alignment of the beam to hit the nominal center that I think was also used in the old system. And finally, there's a macro view here where one can build up a macro by clicking on these functions over here as it would be and building up the macro that you want. Behind the scenes, this is a spec macro. So there are, if one runs over it, there are the spec commands that are run as part of this. Here to this, let's see here. All right, so that's the parameters that are set there. And that can be saved as a, let me just see here, the exported as a spec macro or as a file, this XICC file. But basically, building up these will allow you to run them and then go away, have your coffee, have your dinner, have your sleep, and then come back when everything has been completed. So this, of course, can be a little bit time consuming if you have a very, very long recipe. The advantage is nevertheless that you will not make spelling mistakes as you go through this, and you will immediately be able to sort of go from clicking things in interactively and to building up your macro. Let's close this here for now. So the first thing on our sample is a sample viewer. At some point, you may have an image of the sample. Of course, you have to move the camera around to make sure you have a vision of this. We worked a bit with this, and this beam is where we believe that the sample is going through. There's sort of a parallax going through here, so this is hitting the back of the side here. But in any case, the first thing that you want to do and can do is you can choose the plate that you have in there. Let's say that you had the Lincoln HFSX. All right, once you have that, you get a drawing of that coming up, and you get a list, you get green points of where let's say the points of interest are. Here's a point that's the sample, and here are possibilities for calibrating this particular stage. Now, there may be, this is intended for the Zeus 3, so in terms of the drawings, there may be some differences in there, but certainly the main point is there, and that's the adaptation that you'll have to live with at this point. But let's go back to the calibration plate that we had here. All right, so that's the first thing. Just doing that actually does nothing except change the picture in here. If we really want the system to go to this, we go here and click there. So now that's taken in, all the parameters, particularly to that stage, are read in, and we're ready to go. Now, let's say that we wanted to make one of these locations, or a location that we had, tell that to be 0, 0. That's something that you do. I know on the old system, you align the system, you find where the center hole is in 0, 0 position, and then you set that to 0. Well, you can do that here at calibrate 0. Now, I'll just have you notice that you are at x minus 11 and z is 0. So this is definitely not the 0, 0, but we can do it. All right. And so the 0, 0 is defined in this drawing as that reference point in the middle, and that's where that action would be to take you there. So in any case, the methodology that you've been using works. You go to the central hole where you want to align, you align horizontal vertically, and then you can set that to 0. However, you can also not set that to 0 and work with it otherwise. Let's go back and say, we now have this stage in here. It's clearly not in that position. It's clearly on this position out here. That hole is somewhere in here. And what we're going to do now is just choose that stage again. So hold on a second. Here we're going to go with a calibration stage there. We're going to choose that stage here, and we're going to now choose a position. This is position A, nominal that it's sitting in. The system then goes back and looks at the reference data. Where should I be with respect to that reference data, and moves to what it thinks is the nominal 0 position, which is exactly what it is. Now that depends on that relies on the stage having been properly homed, and there is a simple homing function that I'll show at a later point, not during this tutorial, that can get that homing back. But basically, the idea is that if you take a new stage in, you would choose the stage here, whatever that stage would be, the 15-hole stage. You would choose the configuration here. and then it would move to the 0, 0 position wherever that would be defined. A lot of these stages have the 0, 0 position in the same position, so it won't look like it's changing, but others won't, like the Lincoln, for example. So again, you choose the calibration plate, which is what we have, and I click on that to make that system known, and then I go to here where I tell it I'm in the position. Hey there. All right, good. Now, again, in this position, I could do some scans. I could do an align hole. Why don't I do that? I'm going to do an align hole. I'm going to scan 2 millimeters by 2 millimeters, and I'm going to just measure 20 points there. So now I've started this scan, and I can just see here that so right now it's moving the beam stop out of the way, and then it begins to do its stepwise scanning in. So this is now displayed in splot. Splot is able to look both at the log file as well as the current scan. It's possible for us to choose any of the counters to display. At this point in time, we're looking at the region of interest. We could also look at the whole detector in addition. Not much difference between those two at this point in time, but those are the functions that we have. This is similar to what you had in one of the Spec FE windows, of course. The align feature, not only does the scan, it also moves to the calculated center using a center of mass approach. We'll just do that vertically there as well. And so what you can see is now the position is not 0, 0, it's 0.061 in the horizontal, and at this point in time, it's going to be scanning in the vertical. So that's you could say that's our scan center. And once we have that, we can set that to 0 or we can leave it. Then it comes up in here, does that scan, and based on that, we have a center. All right, good. And I forgot in this case to reduce the scan, so it was a scan of 4, but it's all right, it'll be fine. Up here, there's some information on this. If I wanted a cursor with information, I could bring that in here, and that centers at about minus 0.1, which is also where it's moved to, and we can see that here as well, minus 0.126. So that's where that center is. We could make that 0. Let's go ahead and do that. All right, good. So now that is called 0. And you can see here now, those are 2 set commands that you would typically do. And but here it's just a click of a button. So now we've got that perfectly centered on that hole. Let's say we want to move to one of the windows. Let's see here. We don't have a point that's defined here, but there's a nice open slot down here. We're going to move there, and we're going to do that by moving a step up here. We're going to move steps of 5 millimeters. 5 millimeters, and we're going to move upwards. So we press the button here. Going to move upwards. All right, good. So this is a little bit small. We can use this here. We can use the mouse scroll button, and we can reset to the center by pressing this little bullseye here. So we're going to go a little bit higher. All right, let's say here, so let's say I had a sample here for some reason. I don't have anything, but let's just say I did have something, and that was a particular sweet spot for me to make. I can make new spots here. If I click here, I give it a sample. Any name is fine as long as it's not one of the ones that's already there. My sample 1. And now, and I can even give it a description. The advantage of doing that description will come into the header file. if I know the thickness, I can give it a thickness. But basically this, and I have here the location. So basically this allows me to generate, sample areas that I want to measure, come back to later and measure. So in that location. So now I can go to that. If I want to, I can click on these others and go to there. Good. I can go back to the one I just created. If there are too many points in here, I can also look at here. I've got these places here. All right, let's go to the glassy carbon. Yeah, let's go to glassy carbon, and then I'm going to go to that. And there I am. So now I've created my little special point, and I can move around on all these different ones. One final thing I want to show you about this panel is that you can also align a capillary, or you can scan a sample. Now, these align routines, they will analyze the data and move to a point that they think is the most well-aligned position. The scan sample doesn't. That just scans either X or Z, or in a cross way. You can do two-dimensional scans or one-dimensional scans, but basically it just does a scan, shows you the output, and or shows you the scan, and then you can decide where to go. Now, once you decide where to go, you can either move with the arrows, or you can use a little feature here that is in this SAXS here, there's a server where you can ask this Z motor. So let's just see, you have access to all the motors. You can ask the Z motor to go to I think the center of mass here. You can either ask it to go to a particular Z, or the peak, or the center of mass, or the center of this here. So you can, so you can do that, and then you press go when you're ready with that. You can also do a scan if you wanted to do that from here, a special scan. So you have those options immediately tied into this, which takes the place of one of those spec windows that was doing similar kind of stuff, allowing you to go and click and stuff. So let's just see here. All right, let's get back to there, and let's take a look at the next part of it. So now we have our samples, and we have a detector which is set up. This detector is set up with no tubes. Once I click this here with no tubes, or whatever tubes I choose, the system is going to say, all right, we now know that this is the sample. We know that it is in this particular configuration, and we now know that there are no tubes. It means that we should be able to get a really good estimate of what the distance is. So we're going to go there, and then the way you do that is actually set. You have to indicate here a collimation that you're going to work with. We're going to work with high intensity collimation for this, and then we're just going to go with that. So this is now doing that at the glassy carbon position, which is fine. As long as there's some radiation that comes through, it's going to be okay. So what it does is it moves the beam stop out. It makes a measurement of the beam, figures the centroid, moves the detector, makes sure that centroid is in that center pixel, or aligns with where it should be, and then it moves the beam stop back into place. And it also gives a position. We have these two tabs here. So this was the method configuration. So here it's like the method is we go by these tubes, and we have a choice of either high resolution, standard resolution, or high intensity. These are not, let's say, the H-resol or the H-flux or whatever that you were accustomed to. These, for each of these tubes, there is a different combination of collimation or slit setting. So a high resolution measurement with no tubes is not the same as a high resolution measurement with the full length. A high resolution measurement at the further distance requires a lot smaller slits, whereas a high resolution measurement with no tubes, you can actually use a fairly large slits. So of course, high intensity has larger slits, high resolution has smaller slits, and standard is just sort of where we would recommend that you would be. These can be changed in the back. So if the instrument responsible wants those changed, that linking up to exactly what configurations they are can be chosen. But anyway, a standard person coming in to do a standard measurement without, on samples that they haven't looked at before, just go ahead and choose standard. So which we chose the high intensity, we chose high intensity, so that's what the setting is right now. Now, there's another tab, hardware configuration. What that says is right now the distance is set to 362. And we are in the ultra high flux configuration. We can, if we have different knowledge, we can tell it, actually, this is really 268.8, 268, let's do that, 268.8. Right? That could be a result of a calibration or something else. But we have that possibility. We can change and update that. There it goes. And once we change and update that, it does the same thing again. It will find it'll find a center, it'll go through everything. And maybe this is not that super relevant because we haven't really changed the collimation, but it does go through that and make sure that we have the correct centering for that distance. And then it records that distance, so that if we later take data, it will actually have that in there. Now, here we can choose any one of a number of configurations. And since the original system was made where there was a couple of these, we have put in a number of additional ones. Basically, this steps from slits that are very, very open to slits that are very, very closed. So, so you can also choose to particularly go to, let's say, a C2 measurement, and you set that, and again it closes down the apertures and sets that collimation, and then we're good to go. So let's put it back to where it was, because that calibration 362 is actually really good. So we'll put it back to there where that is. We're going to change and update that. All right, good. So there we are. All of that is set. We have our samples, we have our distance configurations, we have our collimation configuration, and we're ready to do some data taking. The first thing is we should take a look at where we actually want this. So what we have is similar to what you had in SpecFE. You choose a directory and then a subdirectory that will have your particular data and the name associated with it. So we're in a Xenocs commissioning. We could go up and do a training. Let's do that. We'll go one up here. So we're going to do upgrade training. And then we'll go into here and we'll make one more. We'll call that introduction. Oops. One. So that's good there. And then under that, we're going to have now a samples. First samples. All right, good. So that's that. We can now here determine what we want to do, or specify what we want to do in there. We can give a quick note. We don't have to, but we can give a quick note. And then we can determine whether we want to use both either the SAXS or the WAXS or both detectors. We'll just use the SAXS. Actually, let's use both for now. We can decide if we want to have a line eraser measurement, if we want to measure with absolute intensity, or if we want to measure a virtual detector, or any or all of these. All right, we're just going to go with a simple measurement right now of the glassy carbon for both detectors, measured for 10 seconds. All right, good. So at this point in time, it's saved. The SAXS data is saved with this 0 and the wax is with the 1. We can open up Exact. And for this one here, I would just add to have a little bit of patience. It has this little rotating thing for about 5 or 10 seconds, and then it actually takes about another 25 seconds or so to open up. So once you've seen that rotating thing, just that means it started up. Just wait, it'll come. Almost at the point of where you've given up. Let's see here. It'll come up just as we get to this. So again, we looked at glassy carbon. Here it is. We're gonna, this is a project based, so we're gonna open a new project to work in. We're gonna find the file that we had. We were in upgrade training. Here, introduction 1, first samples, and we see our two-dimensional files. Now, there are also one-dimensional files. They have dat at the end, and the two-dimensional files EDF, again, everything the way it was. And if we press here, we can get some, what's it called? We can get some previews of those in a little window down here. If we double click on it, we'll get it to come up in a preview like this here. So this is the wax, and here we have the SAXS. The 1D SAXS. Now the 2D SAXS looks like this. And let's see here. I think we have yeah, there was a screen effect there. So anyway, that's the 2D SAXS. And of course we have a shadow down here with a mask. We also have a beam stop as well. And so if we wanted to do a proper, completely correct azimuthal averaging, we would need to include a mask for this. For this here, for the one-dimensional, this is what this looks like, fairly broad peaks, but you can see that we can very easily get these images up. If we want to do some more stuff with them, let's just take these two ones and we highlight them both. Sorry, 1 second, there we go. And then right click, we can edit the files, look at what their header parameters are. We can make a new visualization. There they are added on top of each other. Probably some edge effects here, but basically this is that one curve, both SAXS and wax. And we can also extract properties from them if we wanted to. We can add new things like looking at the header property and saying what's the comment in here. Those are glassy carbon measurements. We can say we also want to know the exposure time. Where is that? That's down here, there. And then we'll add another one just to have the detector distance. So that's called sample distance. Where is that? Is it up here somewhere? There we go. All right, and they all show up over here. And if we wanted to, then we can export those to a CVS file and all is good. All right. So here, I'm not going to go into exact data reduction at this point in time, except to say that there are a lot of supporting information here. There is a tutorial of videos which are online. Let's see, they should come up here. A lot of tutorial videos here on how to do the various things on there. This is a slightly older version of Exact, but it's still, the methodologies are still very much the same. There's also scientific documentation that shows to great detail what's behind all of the functionalities in there. And there are some, let's say, some overview presentations that are also available. So we're not going to discard that one. Let's do that here. Click away, go away. There we go. All right, good. So there's a lot of help. In addition to sort of the display features of it, there's an analyze part of it. And one of the things you'll see is down here, there are image operations such as data reduction and calibration. And up here, there are 1D data, such as doing a desmearing off of a USAXS measurement or other kinds of things, visual peak searches as well. So a number of tools are available here, as well as data analysis and so on and so forth. But I think that part of your regular workflow has been to, at this stage here, actually do a calibration with silver BN8, which we can do, which we will do now. This is silver BN8 over here. We can see there. We can delete these here, and then we can set up a small measurement series, which will be a silver BN8 measurement. We're going to go to that silver BN8 measurement. We're going to measure it for 20 seconds. There. We are going to, let's say, do a line eraser measurement for 20 seconds. We won't do the virtual detector. And we will do an absolute intensity measurement also there. And then we'll start this here. So this is going to run through. First, it's moving over to the silver BN8, and we see as it's moving through, we get a little green. Green and white means it's in the process of doing it. Green means that it's done it and it was successfully completed. And then here are the measurements. And if there's anything that is yellow, then there was some part of it that was done. If it's red, when you've done, then it means that it was not executed at all because of some error. So this was the first measurement of the silver BN8. All right, while that's measuring, it's being updated here. So we can see that. Zoom in and zoom out. We can ask for auto levels, or we can have it be just one level for the next measurements as well. So that's that one. Now that we have some data, let's look at that in Exact. So here we are with Exact. Here we have, similar to that extract, also those comments there, so we can see what's what. We have the SAXS data up here and the WAXS data here. So we were going to look at a calibration, which is one of the things that you were using Foxtrot for. For the calibration, we are going to bring over one of these images. Let's see here. We'll take this one there. It's the 2D image, and I should just say we can, if we don't want to work with 1D files, we can just remove them. We'll see only the 2D images. So I think you saw that I brought that over. Let me just take that here, and I'll start that over again. So in the, not in the view, but in the Analyze panel, I can go and choose an image operation, which I will there, and then I will take that first silver BN8 and put it over here. All right, good. So in this case here, I want to calibrate with the rings. And since since I use this tube way and I'm in the number of tubes, I'm going to be close. And with being close, I can actually use the, oh, sorry. I don't know what I did there. Input data. Okay, good. I will do auto scale that, and then I will. All right. So with that, I first have to tell it that it's silver BN8, and then I'm going to auto select. Okay, good. So if I look at that, it's done a pretty good job. There's only right in here around the beam stop where it had a couple of extra points. I'm going to remove those points basically there, and then delete there and delete. And then I think I'm good with the rest of it. So with the automatic selection of points, I can now calibrate this. And this is what I get. So the calibration parameters are, they'll be down in a second. Let me just see here. I'm going to close this window. So the first thing we see is that the calibration the calibration, the optimization of the parameters allows a very, very nice calibration of all the peaks that are visible. And let me just see here. Down here, the calculated parameters, the calibrated parameters, and what we see is exactly 0.362. With these other parameters also optimized. Now, if we had something that was different, we can change parameters and ask to have this optimized. But I really find the best way to do that is to choose the sample stage, choose the configuration, and then choose, is it 0 tubes, 1 tube, whatever, how many tubes there are, and that will get you really close. And if you want to do a calibration after that, that's absolutely fine. Use this tool. Go down here, 362. In some earlier runs, it was just around 361. And so that can be put into here. Let's say that we had come up with 361 there. We could change that. Oh, now it gets put into here. So that's not what we wanted. So we close this and then it becomes reactive. So then it's set to 361, which of course was not the best parameter, but just to show how that works. Let's just quickly go and take a look at the at exact again here, and we will look at the line eraser, these images here. So double click on this to get a view of that, and that is the line eraser image going on. And let's see, the second one is the, all right, and again here. So there we go. All right, good. These different measurements, let's take those up and see. So we have this one there, which we will double click there, and we will add this one to it, and then we'll add this one to it. There we go. All right, good. So right click and then auto scale all. So these first two ones up here were not auto calibrated. Sorry, they were not absolute intensity. The one that's down here is, or at least we indicated that we wanted it to be. So a scaling factor that depends on the intensity has been put in and applied, and that should be correct. Now, let's just see here. If we are just taking this one, that is absolute intensity except for thickness. And let me see here. If we take the, so this does not divide by the thickness because we haven't put we don't have a thickness for the silver V8. So, but it was done with the absolute intensity, and so basically the units out here are absolute intensity multiplied by the thickness. Let's just go through and see with a classic carbon measurement that we did. Actually, let's go back and do a classic carbon measurement. We'll go to that measurement. And then we will do a 30-second calibration. There we go. We're going to take this off and this one off. 30-second calibration. There we go. Right. Good, and that data is coming up nicely. And it's all right. So for the absolute intensity, I think that was the same on the previous system. It takes the beam stop out, makes a quick measurement, finds the intensity in the main beam, puts the beam stop back in, does the measurement, and then does it on the backside as well. So it uses the intensity from that direct beam measurement and applies that as a normalization factor to the data that was actually taken. So let's just look at how that works out. So the data is we're going to go with a 1D data, sure. So the 1D data looks not like that, like this here. So that's the 1D data with a masking effect out here. So we haven't taken the masks yet. What we're interested in is what's going on up here, because that is known to be on the order, or should be around 30 or so for a glassy carbon, between 20 to 30 for a glassy carbon slice. So the over here we can take let's see, a two-dimensional image, and we will take it to here, data reduction on the two-dimensional image 6 here, that one. We'll analyze that, bring that into here. I think if we wanted to, we can sort of take a look at it. Yes, that's the correct one. And then we want to do an azimuthal averaging on that. We haven't given any data about thickness yet, and to do that, we actually need to go into the advanced mode. In advanced mode, we can choose sample thickness. Oops, we want to use the transmitted, so we want to have all of these clicked, and then the sample thickness we want to specify, and this is 1 millimeter thick nominally. And then we also want to specify that the units for intensity are centimeter minus first. And then that's it. Let's run that. There. That is our curve. We've got something down here where the beam stop is at. This is where we see the curve here. And what do we end up with? Something that is a factor 10 too high. Let's see, what did I do wrong? I'm going to go back to that analyze window and see here. So what did I mention as my thickness? The sample thickness was 1 millimeter. Let's 0.1 here. And centimeter to the minus first. And then there. I'll have to get back to that. That worked just before doing this. That is a factor of 10 too large. Where it should be. So let's leave that for a little bit. I'll make a special section on that, showing that that actually does work. So those are the buttons. The line eraser, we saw that. The virtual detector, we didn't see. In all likelihood, you can imagine that it'll work. And absolute intensity. We've seen how the macros work over here. We haven't looked at the source changes, but here we can go to another source, and if we press activate, then it will go to the Molly source. And the Molly source is already aligned, so you should have a nice and working beam in there, and you can work with that beam. It's already been optimized, or at least I just did that. So that should also be that should also be fine and working well. The last thing that I believe you were also doing was region of interest. So we can go to region of interest here. We have access to a number of the different counters, regions of interest that we could work with. We have one for absolute intensity that looks like this, and we have one for and we have one for region for the overall region of interest. Now these are very, very large. You can choose what you want in here. You know, whatever region you want, you can load to help you. You can load an image and that's in the same position that yours would normally do in-house, and then in temp, and then diode 0 here. And that's where that beam is. We can center it on here. Now, our recommendation is not to make this extremely narrow. It can certainly be narrower than this, but really the scattering in your image should be a lot less than your direct beam. And so really, whether there's like 0.5% additional scattering out here will make no difference in terms of the results that you actually get. So we'd rather keep this large and forgiving than to narrow it down. Once you've chosen that, go to apply and close the window. We go back up again, that same image will be there, and we can choose the here. Let's bring that down and center it there, and again. So just on this one, just check that they have in fact been saved. We've had some reports that if you change 2 parameters, even if you press apply, it doesn't really save it until you close the window. So just take these one at a time and go with that. All right, good. I actually think that is everything that's needed to get your first measurements and to look at your first measurements. Data analysis with XACT is a chapter by itself. I will stop this presentation here and then just revisit this absolute intensity. Just before the video, I did it and it worked perfectly, so I just have to look back and see what I did wrong. I may do another video on that to just make sure that that's done correctly. But anyway, hopefully this was instructive and shows you the things that you would you would need to get rolling with measuring on these. Thank you very much.